Hi guys, welcome to my channel. In May, you manage a fund with access to millions of pieces of financial data, stock price, interest rates, inflations, company financial statements, news headlines, social media sentiments. Here's the questions. Could a computer discover profitable investment patterns that humans simply cannot see? Sometimes yes, but there's another question that even more important. How do you know whether the computer has actually learned something useful, or whether it has simply memorized history? The single questions separate successful machine learning models from expensive mistakes. In these lessons, we are going to build an investor's understanding of machine learning, from supervised learning and deep learning to one of the biggest dangers in quantitative finance, overfitting. Let's begin with the big pictures. Machine learning is not magic. It's not an AI taking over the world. At its core, machine learning is simply a collection of algorithms designed to discover patterns from data. Think about an investment analyst. The analyst studied thousands of historical observations. Eventually, the analyst begins to recognize the relationships. Machine learning does exactly the same thing, except instead of analyzing hundreds of observations, it may analyze millions. The goal is simple: learn patterns from historical data, then use those patterns to make predictions about data the model has never seen before. That is why machine learning has become so valuable in finance. Markets generate enormous amounts of data. Traditional statistical models often struggle when relationships become highly non-linear or when thousands of variables interact simultaneously. Machine learning is designed for exactly those situations. So one common misunderstanding is thinking that machine learning replaces statistics. It doesn't. Statistics usually start with hypotheses. For example, I believe inflation affects stock returns. Then we test that hypothesis. Machine learning often works in the opposite directions. It starts with the massive amount of data, then it searches for relationship automatically. Another important difference is assumptions. Many statistical models assume normal distribution or linear relationships. Machine learning generally requires far fewer assumptions. That flexible makes it especially useful for financial markets, where reality is rarely perfect linear. So before discussing algorithm, let's establish the vocabulary. The target variable is what we want to predict. For example, next month's stock return or whether a borrower will default. And features are the input. Revenue growth, interest rate, debt ratio, inflation, market volatility, anything that may help explain the target. The training dataset is historical information used to teach the algorithm. Finally, we have hyperparameter. These are 16 chosen by the researcher before training begins. Unlike model parameter, the algorithm does not learn hyperparameters. Humans choose them. Examples include the type of decision tree or the number of hidden layers in neural network. So now let's discuss supervised learning. This is the most common form of machine learning in finance. The word supervised simply means the model is given the correct answer during training. It may teaching a child mathematics. You don't simply hand them problems, you also provide the solutions. Over time, the child learns the relationship. Supervised learning works exactly the same way. The training data contain both the input and the correct output. The algorithm gradually learns how the input relates to the target variable. Later, when new data arrive, the model predicts the answer on its own. Financial applications include predicting stock returns, forecasting credit default, estimating bond rating, and detecting fraud. So now imagine a completely different situation. You have thousands of companies, but nobody tells the algorithm which company belong together. There are no labels, no correct answers. The algorithm simply searches for hidden structure. This is unsupervised learning. Instead of predicting outcomes, it discovers organizations within the data. One common task is clustering. Suppose a bank wants to segment customers. The algorithm may automatically discover groups based on income, age, spending behavior, investment preference. Nobody programmed those groups. The algorithm found them itself. The difference becomes very easy once you remember one question. Do we already know the correct answer? If yes, it's supervised learning. If no, it's unsupervised learning. Supervised learning predicts and unsupervised learning explores. One answers questions, the other discovers questions worth asking. Deep learning is a specialized branch of machine learning built around artificial neural networks. The inspirations come from the human brain. Instead of using one decision, the model contains many layers of computations. Each layer extracts increasingly sophisticated information. Think about recognizing a face. The first layer may detect the simple edge, the next identify eyes and nose, and another layer recognize the complete face. This layer learning allows deep learning model to solve the problem that traditional algorithms struggle with. Okay, so reinforcement learning takes a completely different approach. Instead of learning from label examples, an agent learns through experience. Every action produces a reward or a penalty. Over thousands of interactions, the agents discover strategies that maximize long-term reward. In teaching someone to ride a bicycle, you don't provide thousands of label examples. They learn by failing, adjusting, and improving. That's reinforcement learning. So now, we arrive at one of the most important concepts in machine learning, overfitting. It means memorizing every past exam questions. You score perfectly on practice exams, then the real exam change slightly, suddenly your performance collapses. That's overfitting. The model learns not only generally patterns, but also random noise. It becomes excellent at explaining history and terrible at predicting the futures. From an investor perspective, this is dangerous. Markets care about tomorrow, not yesterday. Professional machine learning never evaluates a model using only one data set. Instead, we separate the data into three groups: training data teach the model, validation data help choose the best version of the model, and text data remain untouched until the very end. This provides an honest estimate of future performance. Okay, so every predictive model faces a trade-off: bias and variance. High bias means the model is too simple. It misses important relationships. And high variance means the model becomes too complex. It memorizes the training data. The goal is not maximum complexity, the goal is the right amount of complexity. Learning curve help diagnose model qualities. As we provide more training data, we observe how performance changes. A robust model improves steadily. Training and validation accurate gradually converge. If the gap remains large, the model is properly overfitting. Learning curves tell us whether the solution is more data, a simpler model, or a different algorithm. So how to prevent overfittings? The first method is to reducing the model complexity. Simpler models are often more reliable. Many algorithms include penalty terms that discourage unnecessary variables. Only features that truly improve predictions remain. The second method is cross-validations. Instead of relying on one trained test split, the data is divided into multiple groups. The model trained repeatedly, each time using a different validation set. The final performance reflects average behavior, making evaluations much more reliable. One of the most widely used techniques is K-fold cross-validations. The dataset is divided into K equal parts. Each part becomes the validation sample once, while the remaining K-1 parts from the training sample. After repeating this process K times, we average the predictions error. This gives a much more stable estimate of how the model is likely to perform on unseen data. Thanks for watching.